Hi everybody, welcome back to this course on Internet Technologies. I'm Vardan and today we'll be studying about TCP and UDP segments along with the Berkeley socket interface. Let's start by looking at what a TCP segment looks like. A TCP segment consists of a header followed by data. The header carries critical control information to manage a reliable connection-oriented communication session between two processes. It starts with the source and destination port numbers, which identify the processes involved in the connection on both ends. Then you have the sequence numbers and the acknowledgement number, which handle together the ordering and confirmation of data delivery. Remember, TCP needs to keep everything in order. Next comes a small but important field, that is HLen or header length, indicating how long the header is. The flags field contains control bits like SYN, ACK, FIN, and others that control how connections are established, managed, and closed. The window size field helps with the flow control, letting each side specify how much data it can handle at a time. And of course, we have a checksum for error checking, ensuring that the header and data haven't been corrupted in transit. This overhead is what makes TCP reliable, but it also adds more processing and network load compared to simpler protocols like UDP. The first few fields in a TCP header are crucial for identifying and managing connections. The source port number is the port on the sender's machine where the data originated, and the destination port number is the port on the receiver's machine where the data should be delivered. Together, these two fields identify the applications involved on both sides, and the sequence number is also critical since TCP splits large messages into smaller segments. Each one needs a way to identify where it belongs in the overall message. This field specifies the number of the first data byte in this segment relative to the start of the session. Right after that, the acknowledgement number indicates the next byte number that the receiver expects to get from the other side. This is how TCP tracks which data has successfully arrived and which parts are needed to be retransmitted. Next, let's focus on the header length and flags field. HLen or header length specifies the length of the TCP's header in 32-bit words. Since the header can have optional fields, this value tells the receiving system where the header ends and the data starts. Then we have the flags field, which is made up of several important control bits. First, we have urgent. It indicates the urgent pointer field is significant and is typically used for emergency data. ACK is set if the acknowledgement number field is valid and should be considered. Push asks the receiver to deliver the data immediately to the application rather than waiting for a buffer to fill. Reset abruptly terminates the connection, usually due to an error. Synchronize initiates a connection and synchronizes sequence numbers. And finish ends a TCP connection. These flags help TCP manage a reliable and stateful connection from start to finish. Now let's cover window and checksum. These two fields help TCP stay reliable. The window field is part of TCP's flow control system. It tells the sender how many bytes of data the receiver is currently ready to accept. If a receiver's buffer is getting full, it will advertise a smaller window size to slow down incoming traffic. Then comes the checksum. This ensures data integrity by checking for errors in both the header and the data. But here's something very clever. TCP's checksum calculation includes a pseudo header, a portion of information from the IP header, including the source and destination IP addresses, protocol number, and segment length. This way, TCP can protect itself from situations where a packet might be misdelivered by the IP layer to the wrong application. Now let's look at UDP, starting with its segment structure. The UDP header is much simpler than TCP's. It's only 8 bytes long. It contains the source port number, destination port number, length, and an optional checksum. That's it. No sequence number, no acknowledgement numbers, no window fields, no flags. This minimal overhead is exactly why UDP is so fast and efficient. It doesn't handle reliability, ordering, or flow control, it just sends the data. However, UDP does offer an optional checksum to detect errors in the header and data. If an application cares about reliability, it has to implement its own error management system. UDP is perfect for small, quick messages or applications where occasional packet loss is acceptable. Again, like video streaming or voice over IP or DNS lookups. Now, to write networked applications, developers needed a standardized way for applications to communicate over networks, much like how you read and write to a file. That's where the Berkeley socket interface or BSI comes in. It sits above all the network protocols like Ethernet at the data link layer, IP at the internet layer, and TCP or UDP at the transport layer. Now, BSI provides a standard API for application developers, making it easier to build client server programs without worrying about the low level details of each protocol. Whether you're creating a web server, chat application, or a file transfer tool, you'll use socket functions to open a connection and send and receive data and close the connection just like you do with files in traditional programming. With TCP, the Berkeley socket interface behaves much like managing a file. You start by calling a socket to create a new socket, then you use bind to attach this socket to a particular port number on your local machine. On the server side, you call listen to wait for incoming connection request. When a client requests a connection, the server uses accept to establish the connection. And again, on the client side, you'd use connect to initiate a connection to the server. And once the connection is set, both client and server can exchange data using send and receive functions, just like reading from and writing to a file. Finally, when the communication is done, either side can call close to just end the connection. For UDP, things are even simpler. Since UDP is connectionless, there's no need to establish or maintain a connection between client and server. You don't call listen, accept, or connect. Instead, you directly use send to send data to a specific IP address and port number, and receive from to receive data along with the sender's address. This simplicity makes UDP fast and lightweight, perfect for quick one-off messages where speed matters more than reliability. What's neat is that the Berkeley socket interface supports both UDP and TCP in a consistent way, letting developers use the same general approach for different types of applications. With that, we've come to the end of this lecture. In the next one, we'll get started with addressing and routing and how IP layer ensures that packets are routed or forwarded in the correct direction. So thank you for joining in, and I'll see you next time.